In this segment, we'll finish our walkthrough of the example JDBC program, looking at prepared statements, generated keys, and related topics. Let's look at the last two methods in JDBC example, which make use of the alternate and generally superior statement class, prepared statement. As you can see on lines 156 through 162, main checks that getCustomer returns at least one ID, ending the program if it doesn't, but note that the finally block down here will be run even if we do a return on line 158. If there is at least one ID, then main uses the first one arbitrarily. Hopefully that's the only one, but if not, main at least warns the user on line 162 that there are several similarly named customers. Main then calls getPrefs, using its return value, which is a list of product types, in fact, in the line 163 for each loop, which finds and iterates through all of the products that have been purchased by the customer in question. So going up and looking at the code for getPrefs, we can see that on lines 80 through 83, one big call there, it calls prepare statement to create a prepared statement. Now, per earlier discussion, a prepared statement is created with a SQL string, starting here and ending all the way out there. And the SQL string is the only SQL command that it will run. But as you can see on line 82, right there, the SQL string may include question markers, indicating spots that need to be filled in. In our case, we're using a question mark for the customer ID. Now, these parameter markers, as they're termed, may be filled in and the resultant SQL executed in as many different ways as you like. So a prepared statement is really a SQL statement model or template. Line 84 calls setInt to fill in the customer ID parameter, making PST ready to execute. Prepared statement has a list of set such and such methods where such and such is some parameter type. Each takes a parameter index, one-based of course, and a value of the type in question, an integer, CID in our case, and it sets the parameter in the SQL to that value. Now, question 1. Look over the suite of set such and such methods in prepared statement. You should find that it's a lot like the get such and such methods of result set in terms of types. What would you do if you had to set a blob type parameter, getting the binary blob content directly from a file? No loop, not even an explicit file read command is needed. This can be done in one line. So coming back from a pause and looking here at the API docs for a prepared statement, what you'd want to use is something like a PST dot set binary stream, and then pass it for the input stream, a new file input stream, for instance, that is reading from the file in question. The set binary stream method takes an input stream and reads it to get the content for the parameter in question, which could be a blob or a var binary. Now, once all parameters are set, we run the SQL via the execute query command, or we could have used execute update for an insert, update, or delete command. Execute query returns a result set, which lines 87 through 89 iterate, and in each case they create a new product object and add to it the list, or add it to the list of returned products. In this case, our rows have 5 columns, and we're using 3 different getX, get some type methods: get string, get int, and get date, to get the respective columns according to the correct types. Briefly, by the way, the product type is up at the top, and as you can see, it's really just a carrier that has the 5 relevant pieces of data for a product and a constructor that sets them up. Now, note, by the way, that the product list that we build this way will be ordered by quantity in descending order and secondarily by product ID. And this is not because we sort our return list anywhere in the Java code here. It's because the SQL has a order by clause so that the rows are returned pre-sorted. JDBC code often has a choice between sorting and filtering data in Java on the client side or doing so via SQL commands on the DBMS side, and the latter is usually the more efficient choice. Now, just for the record, we could rerun PST with different parameter values by doing another pair of setInt and execute query calls. A prepared statement may be rerun as many times as you like with different parameter values each time. Prepared statement is implemented so that any string type parameter is implicitly escaped, preventing SQL injection attacks of the type discussed in earlier topics. Statement, by contrast, can be vulnerable to injection attacks unless the SQL string given to it is carefully escaped by the Java code. For this reason, prepared statement is preferred when parameters are filled in with any user-supplied string data. The SQL for a prepared statement is also usually parsed and optimized just once on the DBMS side when the prepared statement was created, no matter how many times the prepared statement is subsequently executed. So for frequently executed commands, prepared statement is also more efficient. So returning now to main, we can see that lines 163 through 165 iterate through the result of getPrefs, printing it for the user to look at. And then lines 167 through 172 prompt for a series of product IDs and put them into purchases, which, as you can see declared up here, is a map from string to integer holding keys that are product IDs and then values that give the count of how many of that product to purchase. Note that lines 170 through 171 here either enter a new product ID with a count of 1 or find an existing entry and increase its count by 1. If there are any purchases, then line 174 calls makePurchases to create a receipt row and corresponding line item rows for the purchases. And makePurchases, going and looking at its code, just for variety, uses both a prepared statement and a statement. Lines 110 through 113 here set up a prepared statement for an insert command to insert the new receipt or create the new receipt entry. That command is missing only the customer ID, and that is supplied on line 112 here. Line 113 runs the insert statement and tests the return value to see if a row was inserted. Recall that execute update returns a count of the number of rows inserted, updated, or deleted. If one was, then makePurchases adds line items to the receipt down here. But it needs the ID of the new receipt in order to do that. We'll be holding that in RID here. And note that the insert that created the receipt inserted only the purchase date and customer ID fields. It left out the ID field. Question 2, just for review, what value will the ID field of the new receipt get if it isn't explicitly listed in the insert? And coming back from a pause there, well, ID is an auto-increment field, so the new receipt gets the next ID value in sequence. Letting auto-increment ID fields set their own values instead of supplying them explicitly in the insert is good design. You generally don't know what the right next ID value to use is anyway, so it's better to let it be auto-assigned. But this raises the question of how to determine what ID values were automatically assigned to the new rows. We could query for the just inserted rows to get their ID values, but that would require a where clause that identifies them, and often the only reliable means of uniquely identifying the new rows is by their IDs, the very thing we don't know. To solve this, JDBC lets you specify that the auto-assigned IDs be recorded and made available via a result set, which you may traverse to get the IDs. Note that the line 110 through 111's prepare statement call here has a second parameter, and that indicates that we want the auto-assigned IDs, or the generated keys in JDBC parlance, to be returned. We'll get the returned generated keys via this getGenerated_keys call on line 119, or 114, sorry, which returns a result set, RST, that has rows with a single column. Each row gives the new ID value for a new row that was added by the most recent update query. In our case, that's just one row, so we do a single next to prime the pump, so to speak, and then we retrieve the one column from the one row in RST, saving that in RID. Okay, now that we have the needed receipt ID, we'll build a single large insert statement to create all the line items with as many values vectors as there are new line items. Lines 106 through 107, reading from the inside out, create a new string builder with an initial content that would be the prefix of our desired insert statement, without the value vectors just yet. Now this string builder is in turn passed to a formatter as its output target. All calls of fmt.format will write to that string builder. Since fmt.format works just like system.out.printf, we get nice, powerful formatting for our values vectors. Lines 118 through 120 or so iterate through every entry, every key value pair in the purchases map, and they call fmt.format to write a parenthesized value vector for each product that was purchased. This fancy question mark colon here, by the way, prepends either a space or a comma before each vector for the %C format specifier. Then after that, we give the receipt ID, the line number, which we just increased for each new line item entry, the key of our entry, which of course is the product ID, and then the value, which is the quantity to purchase. Now once the insert statement is completed, then lines 122 through 123 create a statement and then use it to execute the insert command. And so we come to question 3 here. You should be able to decipher this big if statement that runs from line 123 down to line 132. Note that it illustrates how a single statement can be used for several completely different SQL commands. What does this entire if statement accomplish and test, aside from the already stated execution of the insert statement up here? Well, coming back from a pause, it checks the result of the insert, first of all, to be sure that it matches the number of purchases. The number of affected rows is equal to purchases.size, and that would indicate that all value vectors were successfully added. It then runs an update that sets the extended price field of the new line items, and that again should produce an affected row count equal to the total number of purchases. And then finally it runs an update that sets the total of the receipt in question, which should produce an affected row count of 1. Now, if any of these fail, then the code throws a SQL exception. And note, by the way, that our variadic closum makes it easy to close all 4 closable items, including even the formatter, which should be closed to properly wrap it up. All closum expects is objects that have a close method to call. Now, this wraps up our JDBC example. All the JDBC basics are in this program, including setting up connections, using the 2 types of statements to do queries and updates, obtaining generated keys, walking result sets, and closing resources. Now, there's a good bit more to JDBC, but these topics cover the majority of what you'll use in most JDBC applications. So now that we have a picture of how one interacts with a database from a program, let's look briefly at the contexts in which such programmatic interaction is useful. SQL is already a powerful language for expressing database queries and updates. Indeed, if you look at it from one viewpoint, our JDBC example program is really just a text UI that automatically performs SQL operations in response to user input. It's kind of a glorified go-between between the text and the user, the text from the user and the SQL. The same might be said for a web service that uses JDBC to perform database operations in response to web API calls or page hits. Many such services are really just glue to translate HTML, HTTP requests into SQL actions. So is that all there is to programmatic database operations? Or are there cases where the computational power of a full programming language is needed in addition to what SQL provides? Here are a few more powerful examples. Let's start with generation of test suites. In labs thus far, you've probably hand-generated test cases for the SQL operations you are working on. But imagine having to test a large database system with sample content that offers various complex scenarios. Would you handwrite huge SQL files filled with insert statements to populate the database with sample test content? Any serious automated test of database code requires programmatically generated test content. A JDBC program that automatically produces such content in arbitrarily large volumes is one good way to do this. Example number 2 are computational tasks that are beyond the capacity of SQL. Any computationally intensive software that works with large bodies of data will almost always use a DBMS to hold such data, as opposed to storing it in flat files or hierarchical directory structures. The power, reliability, and efficiency added by the DBMS are valuable, even if SQL is insufficient of itself to perform the computations needed. Examples might include academic course registration, accounting and inventory, bioinformatic analysis, and of course any big data statistical analysis. All these use very sophisticated code in standard programming languages to do the serious work, and they use JDBC or some other API simply to read and write data to their database storage. And let me insert here a third item, which is traversal of graphs and networks, a special but remarkably common case of a computational task beyond SQL is that of traversing graphs or networks. Say we represent friendships between users in a social networking site by an end-to-end relation of the user table to itself. We might represent the relation by a friendship table with each row in friendship connecting two users via two foreign keys, both referencing the user table. In this scenario, finding the degree of separation between two users, the number of friendship relations you must chain together to get from user A to user B, involves a graph traversal, using either a loop or recursion, running to arbitrary depth in the graph. SQL can't do that. You need a full programming language. And this issue comes up in many other contexts. Graphs are pretty common, whether they represent friendships between users, flights between cities, prerequisites between courses, 1,000 other examples. Such graphs are easy to represent in a database via an end-to-end join table representing the edges in the graph, but doing analysis and computations on the graph requires more than SQL. And the third example is database sanity check and repair. Large database systems like websites often have sanity checking programs that run in the background, looking for evidence of inconsistencies or errors in the database that were introduced by bugs in the main application, and reporting or correcting them. Most DBMSs offer triggers, a means of specifying SQL checking or updating actions to be taken when certain changes occur in a given table or column. These are highly useful for ensuring database integrity, and we'll cover them in a later topic, but they aren't always adequate, and inevitably a full programming language is needed for some integrity checking or updating applications. Note that all of these are examples where programmatic database control beyond just SQL is needed, but not necessarily examples that must use JDBC. JDBC is just the Java solution. Almost every major programming language offers an API for database interaction, sometimes several of them. And most DBMSs also offer their own SQL-based procedural languages in which you may write stored procedures, blocks of true code with loops, if statements, etc., and SQL embedded within them. We'll look at stored procedures for MySQL in a later topic. Now, whether you use JDBC or some other API or stored procedures, there are cases where SQL is just not enough, and you need the full power of a programming language to get the database job done.